Basically, one of the nice things of working together is that take derivatives in space becomes multiplication by the variable. So versus inequalities say more than that. If the function is localized in the frequency space, then taking derivative is just multiplying by x. So this is basically what the proposition that I'm going to say, and we will draw it because it's the main step of the distribution. So let B be above. And C and in RD. Now let P and Q between 1 and infinity with P less than Q. Then we have if our function has a Fourier transform supported in the ball, then the norm of the derivatives. Okay, so this just means the norm of all derivatives for the case is less or equal than some constant. This is if it is supported in a ball with some dilatation. Okay, I will see how this factor. What do you think of one? Okay, I will not move I want to fit both and then say the dilatation and same for the. Then we have k factor of this. Okay.
Someone saying the resolution is not good, it's too low.
Maybe it's the connection. You can also zoom in.
Oh, yeah, that was better.
And the second part says that if the support is contained in an atom, then it's not only less or equal, and we have the equivalent. Okay. So for the proofs, the first thing I will do, I will remove the lambda here. Basically, we can do everything with lambda equal to 1, and for general lambda, just work with the dilatation. So this we don't use generality here by just working with dx equal to Euler. And just plugging this here, you obtain this the lambda to the power. Okay, so the first part, the first proof, because U is both in the box, let me construct the function P, which is completely supported in RD, and such that P is 1 near the box. Okay, and this is just because then the Fourier transform of U is exactly equal to P times P. Well, now we are almost done. Because of this, we go to physical space. Then U is just the convolution of G times U with G inverse of 5. Take derivative. This goes into T. Now that's inequality. With here, 1 over 2. And finally, we just need to see that this is in an R. And just a consequence that G is the inverse Fourier transform of this function, which is completely supported as infinity. So I will just write it once. I will not do it in the second part, but we can bound the R norm by the infinity on the L1. And for the L1, we split the integral for a small x, for large x. All this is smaller than this in an infinity, and this comes from the part of the integral of large x. So we need this decay. And now we move back to Fourier. Okay, now for the second part, we do something similar. We construct phi with phi equal to 1 near the annulus, so that U, let's call this P tilde. This one? Yes, so for P, maybe I should mention on it, no? Like everything that we're going to do for the space is a natural generalization from L2 versus L2 sort of space to L1. And most of the things for L2 are simpler than for L2. Okay, I was saying this. We only need to prove now this part here, the one above we already did. So I want to put derivatives in U here. I will do that by putting derivatives here, integrating here. And I will just mention that you can check this formula which is just computed. This is equal to some sum. These are just some numbers. And we will use, we use this this identity so that we can write ut equal to this sum. And we want to put k derivatives in u. And all the rest apart. And because I'm adding this, I have to multiply by inverse of this. Okay. This partial. Okay, and here I can do this because phi is this is not well written. This is supported in the arguments. What's G alpha here? What's G alpha would be the inverse Fourier transform of all the rest. So A alpha minus H alpha and here I should say that phi is supported in the argument. So there is no problem at all. Okay, so we see that, as I said at the beginning, if we have functions localizing frequency, if the Fourier transform supported in annulus, then taking derivatives is multiplied with maximal. In general, we don't have functions supported in all or in annulus, so what we want to do, and this is the little position, is take the function, go to Fourier, and split it so that we have pieces supported in annulus. This is the proposition. I will not prove it. The proof is by construction. I created the function that I need to say and check that it satisfies all these properties. So we have that there exists two regular functions. X so there exists radial smooth function compactly supported in the whole. It doesn't matter this number here. Let's choose 4, 3 so that everything is regular. You can put the middle here. And 5 in an annulus. And okay, I don't remember the numbers for this annulus, but such that they satisfy the following products. So if you add all of them to scale, Then this is the regularity. Now, if we want to work without, so if we want to exclude the origin, for example, if we want to work with homogeneous spaces in a solid, then we also have the equality. We have all of them, so also for negative j. This is also equal to 1 for C outside of the outside of the. Then, very important, these pieces are almost orthogonal. So they only touch if they are one j distance. So if this is bigger than 1. Then the support context. And well, for this, you have to choose here R1 and R2 uppercase. What else? Okay, same property. To write same property with the x. Okay, the x only intersects the case j equal to 0. Okay, so the picture that I'm to have in mind here is that we have x e and then all the others are regular. So symmetric here.
I was thinking around 1/2, just more around 4 for 2.
Sorry, yes.
It depends either on 1/2, so 0.4. Something is more than 4.
Okay, that's what we need. Yeah, we need also visual properties. If we add these balls, obviously, the ball is an annulus that does intersect the ball, and of course, this is an annulus. And then, for case sufficiently far apart, then to analyze and this I will use this later when we start doing all this. The last property to mention is always I want to define basically more notation that I will use. So I will call H the inverse linear transport of the X and H theta the one of us. And then we define homogeneous magnetic blocks.
Can I ask a question? Is that one half or 1/4? Or is it important?
It's not important, and I think it just depends on the choice that I made. I think for this question it was 1/2, but I don't know. Basically, I just need here one and one. Yeah, I can check what
Each point with one the next. If they sum to one, they will do 1/2 each.
That we I didn't check. I just looked on the mobile. Maybe just in case. Okay, so the definition of this is just the cutoff frequency and cutoff operator. So we only take frequencies up to J-1. This again, I just need to choose one number here, so J-1. And everything, we can also work with the homogeneous one, which are just defined all of them in the same form. It's in the past. And in this case, the cutoff operator we need to use the boundary. Some comments. Well, by construction, at least formally, the sum of everything is the identity operator. Same for the homogeneous one. And maybe a comment of why we took smooth blocks instead of choosing, for example, like the characteristic function, like this, which in that case we would have an orthonormal decomposition. The thing is that from the ones that we have, it is true that the LP norm of the blocks is less or equal than the LP norm of U with a constant independent of it. If we use this one, then that is not true. If we use blocks like this, let's say L tilde J, defined by taking T tilde Then this is not true, and more or less the reason why is that okay, just briefly I will write it. So we can write this characteristic function in terms of the sine function. What happened?
This parameter.
Oh no, so this is the notation that I wrote. So this is a notation to mean that this is the inverse Fourier transform of the variable. Yeah, I will usually write the full thing, but sometimes. Okay, so I was just saying that if we take this kind of cutoff functions, then one can see that this can be written in terms of the sine function, and from this you have Hilbert transform appearing, and then for the Hilbert transform you have boundaries of the LP norm, but the constant here depends on P. And more or less that's why if you choose this, you cannot have a constant independent of P, that we will need in this. An additional remark, we can, like classical spaces, like solid HS and Felder C alpha with alpha positive and not an integer. Have a very easy characterization in terms of this block. So, for example, for the one in Sobolev is very easy to see. This one, the one in Sobolev I just mentioned, but I will not do it. The one for Sobolev is just a consequence of this inequality. So the homogeneous Sobolev norm is just so do the same here, like multiply by the factor, integrate, and we obtain that C2 UHS squared is less or equal than the sum in J of well, I could write here this, but since everything here is supported on the blocks, we can just put here to the X. So here I'm saying that the X norm of U is equivalent, that form is equivalent to the L2 norm of the X. I just mentioned that I will prove the C alpha norm is given by the system in J. This, well, it's longer than that, but it's basically using Taylor's formula together with the Bernstein inequalities. And well, if someone wants to see it, you can just Google it or in the book by Shan, Bakuri, and so with all this, let's define the best of the spaces, which are just a natural generalization of this group. I will define the relativity norm U B P Q S, so the best of the space with S derivatives and P integrability is defined by the LQ norm outside S derivatives each block mentioned in LQ. And the main classical spaces that are contained in this scale are the Sobolev Portuguese and K. There is another family of spaces that we will not really we will not use them, but I think they are natural from this definition if we exchange this, if we take first the small and I just mentioned this because this family of spaces include the classical LP solar space. For Q equal to 2 and P equal to 1. In particular, for P equal to 2, both spaces, like you have both best and very solid between sides for P and Q equal to 2. I will mention very few properties of vector spaces, and basically the ones that we need for the Navier-Stokes result. So I will not mention that we have binary spaces and that smooth compactly spot that dense and all those kind of properties. I will just skip. So I will just mention some embeddings to compare them with the spaces that we know, and it's embedding and interpolation inequalities. And even for embeddings, I will just mention some of them. There are many more that one can look up. So, well, the first one is trivial, which is just a consequence of the embeddings of a small LQ. So this is just from this embedding. Then the classical Sobolev embedding, the general Sobolev embedding. And here we have to preserve the differentiability index. With increasing P. What else? Yeah. So the ones with third index 1 are bounded and continuous. And in general, for vector spaces, the important values of Q are usually for 2, if we want to recover solid. 1, because of this kind of embedding. So for 1, we usually have some continuity. And infinity, where bad things usually happen, but they include a bigger family of functions. So for example, characteristic functions, if you put Q equal to 1, usually they don't belong to that space. If you put infinity, then they are in the space. There is almost nothing to prove here. Both things are consequences of Bernstein's inequalities. Good. Let's invite there. So, for example, this one. So here I'm saying that S2 is this quantity. So let's do the LP to norm. And we saw at the beginning of the class, here we have the scale, so 2j to the power 3. And then we have 4. And for 3, so d over p. Now we can take, let's say I'm saying because u was in bp1 d over p, we can add all this. So I'm saying that the series converges uniformly. I mean, they are continuous and converge uniformly, so we have and they are bounded. Okay? Each, well, we put it here. No? Each one is bounded. Each block is continuous, and we have the boundary. So we have the. Okay, I finished solved. Now, let me make some estimates. Yeah, so I will just briefly introduce partial differential calculus. Basically, the tools I will use for the presentation. So all that we introduced, like the main goal was that in the end, for Navier-Stokes for other PDEs, when we want to estimate nonlinear terms, in critical spaces, in a test, we have to take fractional derivatives of nonlinear terms, and with classical proofs, usually it's not easy. By this, because we have these moving derivatives, just like moving factors of 2j constants, everything becomes easy. And we will see that I will prove two basic estimates, and then as an example, I will just show one elementary estimates in this with this proof that it's not easy usually. So, okay, we have from the triadic decompositions, this formally U that's equal to the sum of all the blocks. Same for the function B. And now we're going to start the product U times so again, all this formula we can just almost there. But moreover, we can introduce the so-called volume preposition, which is just group these terms nicely. So take the low frequencies of Q together with the high frequencies of B, the symmetric part, and then the remainder when both U and B have similar frequencies. So this is the paraproduct of B by U, I define it in moments. The symmetric one, the paraproduct of U by B, and the remainder of B. We work now with homogeneous, but basically most things are the same. So as I said, the product of B by U is low frequencies of U. I mean, low frequencies compared to the frequencies of B. So low to high. Because remember the low frequency. So there is at least, and that's why we put -1. There is at least there is more than one column. Well, the symmetric I don't need to write it. And the remainder, which is when the blocks are at the same level of frequency. Okay, so now what I just want to show is some estimates for this and some estimates for this. And we will use it as well. We need to figure out some more small experiments. Yes, yes. Yeah, because I'm working with the so here this is in C, this is J. Well, in C, I think this is. Okay, so now I will do two propositions to estimate, and we will use them as black boxes, maybe some parts today and the following. I start first with the parabola. Let me check on the index. We have so in both cases, what we see that for U, when we are using that in the paraproduct, we only have the low frequencies of U. So we are taking the infinity, or if maybe we want, norm, which is even lower than infinity, like this is a negative lower. And in general, for the paraproducts, and I think this is always true, you cannot expect better regularity than the regularity. You can increase, basically what we're doing here, no? You can put more regularity of P than for the product if you have enough decay for you. And something that is usually very annoying is that here T is strictly negative. So this is not true for T0. The only case that you can include for T0 is electric, not the rest of the norm. Okay, so let's start with the first one. Well, so we need to write the definition. Okay, so let's focus on this block. Now I put the definition of the paraproduct. This is J prime, okay, that's a different index. The prime of P. And now this is a property I mentioned at the beginning that we will need. This is supported in a ball. This is supported in an annulus. They don't intersect. So all this is supported in an annulus. So for J sufficiently far from J prime, if all numbers are okay, this should be for this bigger or equal than 5, but otherwise just some number here. We have that delta J applied to this quantity is 0 because the support, the intersection is empty. So in this sum, we only need to consider the opposite of this, so J and now, well, again, this, it doesn't really matter if it was 4, 3 or so. In all the cases, what we have is that that J prime is approximately equal to J. So we can do the same estimate, like the same, basically the same estimate 4 times. So I will just take the LP norm here and do it for one case when J prime is equal to J. Otherwise, it's just like a factor of difference. This is less or equal some constant. The LP norm of the block is less or equal than the LP norm of whatever it's applied to. And now LP, L infinity, LP, because we want to in the end have the best of a space with the LP in D. And once again, we use Bernstein. This is supported in a ball, so the L infinity is just bounded by the L infinity. There are no derivatives. So we conclude. We put this back into here. This doesn't depend on J, so this goes out. We have the L infinity norm of U and the definition of the B, P, Q, S for D. So basically, the only trick was here, and this was a consequence of the construction of the big flux.
For the second one, the next inequality, the constant still depends on J, it depends on the radius of the ball.
No, the constant, no. So in 1 second. So no, the inequality was for the one in the ball, for example, if U was supported in this ball, then DKU LP
And it was K to the power.
Okay.
Sorry.
and where there was another factor, it changed. Okay, so for the second one, I can use everything that I done there up to this point. Okay, so I will start from this inequality. Well, here there should be no prime. No? I said that J prime was like this. And, I'm looking now for this estimate here. So I'm going to write this one. We have S plus T derivative. And the S derivatives, I want to put them with the B. Yes. Where is we need okay, and now the S derivatives, I put them here. So the T to the I mean, this is the next thing. The derivatives are extremely easy to move from one place to another. Okay, so we need to deal with this part here. This is already okay. Looks like what we are looking for. So for this one, let's write the definition of S. This was the sum for all frequencies and more than that. And well, the only problem here is that this is in J, this is in J prime. So these are not really derivative of U. So let's just put them. And now combine these ones. So this is J. T was negative, it's really negative. J is bigger than J prime minus 2, so this quantity is negative. Yeah, I need to put. I think the conclusion is already clear, but now I want to put all this here. I want to take. Okay, I will write it. No, we want to do LQ norm of all this. And Q is less important. Now I'm plugging this here. So P yes. Okay. So we have this and this. Let me put this one. I wanted LQ2. And for the first one, then I have to put LQ1. We have a convolution. So LQ1 again, L1. And this summation. So U B T infinity 2.
All these constant variables.
Yes, I'm not trying to T and S. Not okay. In particular, this one depends badly for t equal to 0 to equal 1. And the comment, like this inequality might look bad or useless because we have a space with negative regularity that usually we don't want, but remember that we have all this embedded. So in particular, we had this would be d over t. Right. Okay, so I finished with the following proposition, the one for the remainder. S1 and S2 real numbers. Now, all the exponent Q1, P2, Q1, Q2 between 1 and infinity, and P given in terms of P1 and P2, same for Q. This just comes from Young's inequality. And then we have, if S plus 1 is strictly positive, then we can move derivatives without problems in the remainder. In this sense, the remainder is better behaves than the paraproduct. We can move the derivatives in the way we want, but we have this restriction. The remainder is not always well defined, in particular if the regularity is negative. In the case that it's positive, there is one inequality. I mean, there are more, but one has to work harder to get them. So if this is just non-negative, then for Q equal to 1, we have so we only have it like the inequality, putting here infinity. And if you check the embeddings, we cannot put nothing on the left. Sorry, we cannot put, we cannot put nothing on the left. No, the embedding works the other way around. So we only have it for infinity. But the proof is the proof will be simple. Okay, we need to use where things are supported, and then start moving derivatives and distribute them in the nice way. Q is 1. Okay, so this is weird maybe, but here, so Q1 means that if you want, I can just remove this. Okay. So yeah, otherwise it looks like this is a 1, or this is the inequality that we can prove. Now remember the definition of the remainder was the argument of the finger. So this is a double sum in J and J prime. Satisfying this condition. And we can also write this as the sum in J. And then I put the new index. And for this part. So now the thing is that this is supporting an annulus, this is supported in an annulus that intersects with this one, so this is supported. In a box, okay? In a ball with basically very useful to the J. So then, because this is supported in a ball, when we put the diagonal block, which has a support in an annulus, for A prime being up, say bigger than J plus, okay, some constant, I don't know if this is 5, maybe it's again 5% less. So for J big enough, then J prime of Rj easy. And this is before explaining with the where things are supported. Yeah. So in this sum, we only have to keep the opposite, like J prime less A prime. And there is a I keep this block. You yeah. Now it's all no, we wanted to split everything equally, so P in P1 and P2, Q, Q1 and Q2, and the derivatives. So, I mean, the important condition will be this one, the J prime less than J. So that we can now artificially introduce it. So then P is the P1 and P2. I'm missing the question. We want S derivative for U. Sorry, S1 derivatives here, S derivatives here. After. S1 plus S2. So this is what we want to know. And so far we have that. This is let's recall this thing with the power. And this is the trick that we did before. So we have S1 derivatives with U, but not really because this is J prime and this is J. But let's just put them. There's one and remove it. And we see that here we have J prime minus J, J prime minus J is smaller than some quantity, so we can add them, or we can like the sum will over. And same for B. Okay. I'm going. I don't repeat it because this is jumps in quantity. And well, I have 5 minutes, so let's prove 2. There is almost nothing to do. Just when in fact, right here where we are, if I try to close it with S1 plus S2 equal to 0, well, here we have 2 S1 plus S2, and this is the crucial quantity. this is less equal than 0. Yes. Okay. So we can add all this. And this goes to negative values. No? If this is 0, I'm using that this is a 2. If this is 0, then everything fails, and the only thing that we can put is L infinity, so that when we apply convolutions in this quantity, only the infinity, small L infinity. Yeah, and I think I will stop here and continue. So the following day, I will start applying all this to prove maximal regularity estimates for the equation and for Navier-Stokes in my critical tests.
The composition. So I'm going to ask it well, to say just like we don't take the joint blocks because then we don't have a smooth function. You see that the smooth function is partition unity.
Yeah.
It was required because we wanted constants which were independent of p.
Yeah.
But if you don't have them, I mean, everything depends on p, I don't think there is a problem except in the end cases, p equal 1 or p infinity, I think the problem is that they are not bounded. The convolution with the characteristic of the anomalous, it's not bounded in the p, so you won't have, for instance, the best inequality.
Yeah, so you're saying that if you don't have the smooth functions and we take the other ones,
You take the other ones,
then for p equal infinity and 1,
you can get figures. But for other things, I don't think there is a problem with different constants. I mean, that this constant depends on p, what's the big deal? I mean, it depends on so many things already.
I agree that I don't see any place where it will take that. But the thing that
You want to work with the scale of p infinity and p equal 1.
yeah, I think so, because I think that at least when I use best spaces, most of the times I'm interested in the case p equal to 1, like q equal to 1 or q equal to theta. At least many places we use those two. Like for example, for singular integrals. The subspaces are so easy. Yeah.